Hello, everyone. My name is Leonid Yurganov. I am from Baltimore. Dustin, Carol, and Hong Zhang are from California. Today, I will be talking about Arctic methane measured from satellites. First, I will describe our methods, including data validation. Also give some information about methane sources, available data on dissolved methane from direct measurements, and main part will be satellite results. Two types of instruments are used for methane. First one is a short-wave instrument, infrared instrument. These instruments use solar radiation reflected from the surface. The advantage of short-wave instrument compared with thermal infrared instruments is that they have a better sensitivity in the lower troposphere. Thermal infrared sensors using emission from the Earth itself has advantage of capability to work day and night, summer and winter, sea and land, and that's why for Arctic we use data of these sensors that will be analyzed later. Satellite data are publicly available, and you see a list of instruments and a list of, together with techniques of retrieval techniques, and for all these techniques, optimal estimation were used, but we had to apply additional filtering. We used data only for thermal contrast more than 10 degrees. Validation was conducted using NOAA flights at three points in the United States. For two layers, for mid-upper troposphere and for red, and for lower troposphere, blue. For two orbital spectrometers, EASI and ES. Lower tropospheric blue data compared with NOAA data show approximately 1/2 of sensitivity compared with mid-troposphere for all data sets. Slope can be called empirical sensitivity because that is a response of retrieval to a unit change in real concentration. So if we use low tropospheric data, we should keep in mind that they are underestimated. A few words about Arctic methane sources, sinks, and transport. Main sources for Barents Sea are geologic methane from deep reservoirs. This methane seeps and dissolves in water, and after that is consumed by bacteria. In summertime, this flux of dissolved methane is blocked by pycnocline and stable stratification. In winter, another barrier appears, ice cover. In Kara Sea, another source of methane is permafrost, and for both cases, methane hydrates. Geography and Arctic Sea. These three maps are for Eurasian Arctic. These two for ice-free fraction. This is color scale. Red is for open water and white is for ice. For 2 years, and below is difference between these two maps. We calculated, we selected three boxes, 2 boxes in the open water seas and 1 box in an area with partial ice. And you may notice that this focus area has maximum change in ice for all this period of time. And this is change of ice fraction concentration year by year. Lots of data about dissolved methane in the Barents Sea. Local sources on the sea floor are clearly visible. Also, you may see high concentrations in deep sea and low concentration near the surface, especially here. This is due to existence of picnic line and stable stratification in August, September. This example is for August, September. In November, picnic line disappears, breaks down, and mixing becomes very efficient. What does AS for this slide see from the orbit? This we separated, calculated mean values for 4 seasons for 2 year-long periods. To adjust for 3 ppb per year global trend, we had to change color scale by 45 ppb. So the same color means difference 45 ppb. Let's look first at summer. In summer, there is a flat field of methane all over the entire Arctic, including even land and water, not much difference. And very different situation in winter. In winter, especially in our focus area, the change between these two years is very significant, much more than 3 ppb per year trend. Now we can calculate linear trend for S for each grid cell, 1 by 1 grid cell. In summer, as you already said before, we see 3 ppb per year trend. For land a little bit more, but significantly more during autumn, August, October, and for oceanic areas, the situation is quite different. The high the much higher trend in winter and also February, April. Next. And what we what we see for seasonal cycle over Barents Sea, it's number 1 compared with number 3 over Norwegian Sea. And this is anomaly of methane between these two boxes and 3 data sets for 3 instruments absolutely independent, and this anomaly increases from summer to winter. These are months from June to June and January in between. It's quite reasonable to compare with mixed layer depths. In summer, mixed layer depths very low due to stable stratification. In winter, it increases and reaches 300 meters. That is the depth of this sea. Now, let's look at trends of methane over 3 boxes, 2 over water and 1 over discontinuous ice. It's northern water and ice. For over water, we have seasonal cycle and winter trend and summer trend, and winter trend and summer trend are close one to another. The same for, or very similar to Barents Sea. For partial ice area, these 2 lines diverge, and as a result of this divergence, amplitude doubled from the beginning of this century to now, more than doubled. And this difference is statistically significant. 4.5 and 3.5. And now, what do we have in the bottom line? Most of methane emission from Barents-Kara Sea occurs in winter after the breakdown of the pycnocline. What is more important, turbulent diffusion of dissolved methane or bubble transport? The pycnocline is not a barrier for bubbles. It's obvious. Therefore, atmospheric methane increase after November should be attributed to the turbulent diffusion of dissolved methane. Third, does the winter flux grow from years? In the northern Kara Sea, the seasonal amplitude has doubled since the beginning of the century, and it is due to winter flux increase. A decline of sea ice cover is the most likely explanation of that. But growing of seafloor sources is also possible, but it has not still proven by now. It takes much more work. And conclusion number 4, 4 years ago, we estimated Arctic Ocean contribution as 2/3 of the land emission. And this is important for the budget of this gas in the Arctic. This, you see the preliminary estimations. And for links to our publications, see the last slide. Thank you.